Designed by ViaSol International, the ViaSol reinforced fill structure has been a revolutionary technique allowing for economical, performing, rapid and easy installation, together with very low maintenance needs. It is used for a wide range of projects, for instance, bridge abutments or access ramps, arch bridges or industrial structures. Installation can take place in all types of settings, including urban, marine, mountainous and flood-prone areas, and it offers excellent performance for poor ground conditions or under seismic conditions. Facings retain and confine the backfill material. Different types are available and can be customized for each project. Concrete facing panels with a wide range of textures, colors and shapes. Steel mesh facings which can be filled with rock for a natural stone finish or fitted with a special surface mat that allow for vegetation. The reinforced fill material meets several requirements such as gradation, shear strength, pH and electrochemical properties. ViaSol reinforced fill structure makes use of fill materials sourced on the site. Combined with thin facings, it dramatically reduces the need for concrete and rebar, making the wall an even more cost-efficient and environmentally friendly solution. The reinforcement elements ensure stability, excellent alignment, and reliable performance. They tie the facings into the soil mass, and they resist the horizontal soil forces generated within and behind the wall. They can either be polymeric strips or steel ladders. The ViaSol polymeric strip reinforcement consists of high tenacity polyester yarns encased in a polyethylene sheath. It acts as a chemical biological barrier against even the most aggressive fills, and it provides the soil to reinforcement shear interaction. The ViaSol steel ladder reinforcement creates the greatest soil to reinforcement shear bearing interaction and pull-out resistance of any reinforced retaining wall system, combining aestheticism, cost efficiency, performance for even the most extreme conditions, as well as low carbon impact and very little maintenance needs. The ViaSol reinforced fill structure is a relevant and proven solution that has been used extensively worldwide and for which ViaSol is able to assist its clients from feasibility studies to project completion.
Great. So this video is using a lot the explanation further. So this would allow us to reduce the system explanation, and we will introduce some system components during the construction process explanation. Okay. Basically, we can repeat some concepts here, but very quickly. ViaSol is a VSL reinforced soil returning earth wall structures. And it's also called MSE. MSE is quite a standard wording to refer this kind of reinforced soil solutions. Reinforced soil walls have reinforcing elements, as you have seen, installed in the soil mass, generating a sort of composite block that takes advantage of the interaction between the soil reinforcing elements and the select granular fill materials. As we have seen in the video, ViaSol system is modular and easy to install, and it can be used for a wide range of scenarios with great response in terms of global cost and construction timings. We will focus on these global cost and environmental issues later on. Okay. So basically, as you have seen, we have different applications in where ViaSol can perfectly suit as a perfect solution: highways, bridge abutments, railways, river walls, marine walls, arch bridges. We will also explain a little bit about this arch bridge solution, and replace classical or traditional solutions for retaining earth, like a cantilever or slopes, reducing sometimes the spacing and reducing sometimes the materials that we need. Different, for example, for embankments and bridge abutments, sometimes direct abutment or also mixing with some pile supports. The main components of this block or these visual systems are the reinforcement and the reinforced backfill. The interaction between the reinforcement and the backfill is what generates this cohesive block. But of course, you need some sort of facing to hold the soil. And in our case, facing can be different types. Partial height concrete panels, which is probably the most popular, most common one. Full height concrete panels, but also welded wire mesh facing and two-stage facing. There are other facings for other systems that visual can also be adapted, like masonry, modular blocks, or rapid geosynthetic, but they are not that popular in VSL. In any case, precast facing panels, in case of partial height, we have seen in the video that there are different geometries, quadrilateral, rectangular, hexagonal, cruciform, T-shape. For the full height, just rectangular panels. We will focus on the construction procedure, which clearly distinguish a lot different systems. And welded wire mesh facing, that as shown in the video was the stone wall, the mineral wall. But if you include some sort of vegetable mat, you can generate this green wall. Actually, the wall is not seen in this picture, but you have to trust me. There is a wall behind the green. Temporary solutions. And with these temporary solutions, we also generate this two-stage wall solution that we'll explain it in the day in Wednesday. As you have seen, there are two types of reinforcement that can be systematically used. Of course, the scenario, the requirements are different. The steel ladders are generating more adherence to the soil, but of course, because it's a steel, you have the corrosion issue. Sometimes the soil is too aggressive, so it's better to use a polymeric solution. We use both steel ladders and polymeric strip solution. The combination between the facing and these two types of reinforcement, it's easy. You just need to change the connection. We will see the different connections that we use for precast facing panels and welded wire mesh facing, attach it to steel ladders or polymeric strips. And Steve, I don't know if you want to introduce this part of reference list. And Steve, are you here?
No, yes, certainly am.
Yeah. Do you want to comment this, maybe?
Yeah, look, I suppose the area of walls is certainly been probably predominantly done by several centres. As you can see, Australia has a fairly large area of wall, India, Mexico. It's been those areas, I suppose, where we've concentrated our efforts, where there is an active market. But yeah, certainly that doesn't mean in other countries that we shouldn't be interested in doing VSOL walls or RSS walls. Anybody can do it. As you can see, CIMI is certainly the biggest region as far as VSOL production. And ALA, is next in line. Sort of the production is certainly, and I think this slide was sort of taken over the production that Australia, I think, had produced, and that certainly was the key. That probably 2010 to 2015 was certainly the time when lots of square meters were being installed. And I'd like to think that we're on our way back up again, where it sits at the moment. We're going a bit faster, mate, for the slides, but yeah, facing without United States. So predominantly partial heights, as Ivan said earlier. The full heights and wire mesh certainly aren't as popular as the segmental faces. Next slide. Sorry. Polymeric strip. So that seems to be more popular at the moment. Certainly not in Australia. The authorities don't like the polymeric strip as much as steel. Yet in other countries, it's the predominant featuring backfill reinforcement.
I can continue if you want.
Okay.
Yeah.
Yep.
One comment here is that because the partial height concrete panel is the most used solution in VSL, we will go deeper in explanation of the construction process and with these partial height concrete facing panels as a basis, because most of the things are repeated for the other solutions. Okay, most of the construction sequence is repeated for the full height and the welded wire mesh facing. We have available different documentation regarding VISOL, several brochures, which are different sometimes depending on the region, but for sure you have checked it, at least one of them somewhere.
That document, just before we go there too, where we're currently looking to update that brochure. So that brochure is 2013, I think. That one there. It's certainly we'd like to think that we could do a little bit better in the last 10 years of updating our brochure. So I hope that will be done this year. That we'll get a new brochure.
We have also available this VISOL reference list that we know it's not fully updated, but we will try to make it update as soon as possible. Also, we have different documents available. Of course, some system components have to be updated, but at the end now we have this system drawings document with more than 100 drawings detailing the reinforcement, the facing, connection, accessories and equipment. We distinguish between accessories and equipment in terms of the accessories are sort of fixed permanent components in the system. Equipment is temporary components that you use and you can reuse in another project. And also we included an interesting assembly drawings that shows you how to mix, how to link between the different components in a single solution. We have the field or reference manual that certainly has to be updated, but is providing you clear basis of the system in terms of all the things we are going to explain in this VISOL course, but with clearly more detail and detailing the geometries and material components and so on. We also have prepared, but it's not ready yet because no time to finish, the VISOL design manual. And it's a quite complete document, but it's true that at least 2 of the 3 standards that are compared in this manual are different now. So we should include update with these new standard versions. And also we would like to include other standards that we will talk later on as the Australian one. And we have also, this is very interesting, maybe Steve, you can explain this better than me.
Yep. So the guys in Spain have developed a CAD drafting tool. So this is sort of an automated version of preparing drawings. We in Australia haven't been able to actually switch our drafting over to that at this stage, but it certainly looks very promising. So this would develop the drawings, just the shop drawings just simply spit out at the end. So you prepare the shop drawing, and where we would actually have to do the drawing individually for each of the panels by the drafting tool. Actually, as soon as you put all the plot, the top and bottom of wall, chainages, alignments, put all the details in, it will actually present you with a fully documented report and information, even down to the BOQ and a report at the end. So it's quite an interesting tool. Some of the information that is on there, I suppose, doesn't satisfy every country, and that's probably more the point why it hasn't been adopted in Australia at this stage. But you know, there's more work to be probably done there for everybody to be able to get on board to be able to utilise that.
So a question can raise now that it's okay, we have our VSOL solution, our reinforced soil retaining earth wall solution, but there are other solutions to satisfy the same function or to solve the same problem, like the gravity wall or cantilever. We can ask ourselves which one is the optimal one, changing, for example, the wall height or changing some sort of component features. So we will see this video now. It's a bit longer, but it's a very, very nice video, okay?
Hello, my name is Vincent. Thank you for being here, and I hope you're fine and comfortable. The topic today is of the utmost importance: how to reduce the carbon footprint of a retaining wall. We all know retaining walls. They're used as temporary or permanent structures along roads, railways, bridge abutments, and arch structures. They can basically be found everywhere. So it's quite useful to ask ourselves, what is the best solution in terms of carbon footprint, right? There are three existing solutions. I guess you know them, but just to be sure, the gravity retaining wall, its name speaks for itself. The weight of its major component, mass concrete, maintains the stability of the wall against earth pressure. The cantilever retaining wall, with its L shape, it is mainly composed of reinforced concrete. The weight of the earth on the horizontal part of the L anchors the structure. The vertical part of the L works in bending to retain the earth pressure. Last but not least, the reinforced soiled wall, which combines two things: compacted granular backfill material and soil reinforcement with precast concrete facing panels. We'll focus on the VSOL solution by VSL and its two types of reinforcement systems, the steel ladders and the polymeric strips. So now that the introductions are made, let's shift to the core of our topic. What is the best solution in terms of carbon footprint? Because methodology is key, and I am adamant about this. Let's compare what is comparable. To be objective, the comparison is based on an identical functional design, such as loading conditions and design life requirements. Are you ready? First, let's look at the concrete volumes. Compared to the gravity wall and cantilever wall options, the reinforced wall uses 50 to 90% less concrete, depending on the height of the wall, since its main structural component is soil backfill. Now, what about the steel quantities? Once again, with soil as major component and also with 50 to 75% less steel, the reinforced soil wall has the best environmental impact performance compared to the cantilever. Finally, let's envision a bigger picture and compare the global warming potential through embodied carbon emissions at different wall heights. We're comparing backfill soil, concrete, this is for gravity and cantilever wall. For reinforced soil wall, this only includes precast panels, including concrete, steel, rebar, and connections. Reinforcing steel, meaning rebar of the cantilever, and soil reinforcement for the reinforced soil walls. And let's not forget construction activities and material transportation. For this exercise, let's say that transportation is based on 100 kilometers for the prefabrication and transportation of wall-facing panels, although it could easily be cast on-site as well. And also 10 kilometers for the backfill, as well as for the concrete pouring, for gravity and cantilever alternatives only. As for VSOL, it is just about transportation of precast panels. So, as indicated on the graph, I think we have an answer to our initial question. What does the graph indicate? First observation, reinforced soil walls like VSOL result in lower environmental impact than traditional earth retaining solutions. It's due to the use of backfill as the principal structural component rather than concrete and steel. The VSOL solution only uses concrete for the thin facings. The use of waffle panels, which are shaped to optimize material quantities, can also be an interesting solution. You can note as well that concrete panels are most of the time prefabricated in a controlled environment with a huge optimization in the production ratios, cycles, material wastage, energy and water consumption. This also contributes to the reduction of carbon footprint. Lastly, VSOL walls generally make use of adequate fill materials sourced on the site, or even recycled or marginal fills, with the aim to continue improving the environmental efficiency. Polymeric is the best low-carbon solution as it uses much less steel for the same strength requirements. This solution can even be less carbon emitting when void-formed connection is used. Second observation. The higher the wall, the bigger the benefits. They increase markedly with walls about 5 meters high or more. In terms of greenhouse gases emissions, at 10 meters, VSOL is 4 times less carbon emitting than gravity and 3 times less emitting than cantilever. The difference becomes much more significant with walls higher than 10 meters. VSOL will be almost 5 times less carbon emitting than a traditional solution. And the polymeric reinforcement is also presenting a much better solution in terms of carbon footprint, between 8 to 9 times less emitting. Did I forget something? Yes, the carbon impact of the maintenance activities. They were found to be negligible when comparing to the full scope of the environmental analysis. And they're basically just about transportation with electricity and diesel consumption. However, demolition is key here. And reinforced soil walls are significantly less impactful than gravity and cantilever solutions. So there's no need to use heavy machinery, and the demolition can follow the same step-by-step procedure as the construction sequence. And maybe even to allow the reuse of some of the components. That's it. Of course, the choice of a retaining wall depends on many criteria, and now the carbon footprint can be an important indicator to consider. Well, I hope I was clear enough today. For more information, please do not hesitate to contact VSL, who is a specialist in the design and build of these low-carbon solutions. Thanks for watching.
Yeah, isn't it?
Yes, yeah.
So, in terms of sustainability, sustainability, as you know, is including not only environmental issues, but also economic and technical functional issues. We have seen that if we just focus on the environmental issues, it's clearly an advantage to use the VSOL solution against other traditional or more classical solutions. But this is not only for the environmental. As long as you investigate the economical issues and as long as you go in a significantly higher walls, you don't need, from 5 meters high wall, you also detect the economical advantages of using VSOL rather than other solutions. An example is that we will explain in maybe a little bit longer the last day, but an example of this is these arch bridges solutions that combine the precast arches, precast reinforced concrete arches with VSOL. VSOL up to the level of the road or whatever. This is a bridge, and we can compare this solution with an alternative solution for bridges, which is the classical solution of post-tensioning viaduct segments or sections with piles. If we do this, if we compare this, and we have done this for a specific project, we can clearly detect that we are saving concrete, we are saving a steel rebar, we are of course saving post-tension because there is no post-tension in the arch bridges plus VSOL. And also we are reducing the works to be done. Okay. Again, we will explain a little bit more this project in the last day. But in any case, to keep it in mind, this comparison is reducing, if you use Visol or we use the arch bridges plus Visol, is reducing about 50% of the CO2 equivalent for the warming potential indicator. So we have finished the introduction. If there is some question regarding the system, not to worry, because the system will be particularly explaining during the construction sequence, and also some components will be explained it now also in the design section. Okay, so I will move to the design.